Multiplayer gaming is a complex problem, and each game requires its own unique solution. In this devlog, I will talk about how I achieve stability for players with lower end machines, utilizing some tricks I created to enhance performance in a multiplayer setting. This video will be about high level concepts and geared towards some of the early to mid level game developers out there wanting to make a multiplayer game, but struggling where to start or even how to think about this topic. Maybe I can give some insight into my thought process as well as some resources for getting started. A note about me: Pandarunium is my first game I will be releasing. I do have a few others I've worked on, and I've gotten a good amount of experience before this, but none of those have made it to release yet. Some are pretty quirky, and maybe I'll make a video showing some of those ideas, their concepts, and why I dropped them. I think there's some fun stories and advice in there. Let me know if you'd be interested in seeing some of those. In my game, Pandarunium, which you should go wishlist and try the demo on Steam, by the way, is a game that requires lots of enemies, and I mean hundreds, to be on a single level in a tightly contested amount of area. The premise of the game was that a panda was running through tons of enemies to get to the metal spiral maze. If the player is hit by an enemy, he drops dead on the spot. A dead player would only be allowed back into the game if the other players ran over his body to revive him, or the other players complete the level, respawning everyone. This was directly inspired by a custom game for Warcraft 3 that had a bunch of players spawned as cats and they would run through the maze of wolves with a high pitched version of Linkin Park's Numb playing in the background. I decided early on that I wanted to make a multiplayer game, but didn't want the cost of paying for servers, so peer to peer networking became my ultimate solution. So one player will be acting as a server, all others will send input to the host player. The host player performs its validations and calculations, and then sends back where everything happens. The hosting player will also be the only one running logic for the enemies and will send updates to the players about the true state of the game. Just for reference, I am using Unity with game objects, sorry, no dots here, a custom networking solution utilizing facepunch.steamworks, which is a C# wrapper around the steamworks.net C++ implementation. And last note, these decisions I made for my game may not be good for all games, or even most games. They were made specific to the needs of Pandarunium, so feel free to use them, but don't expect them to be the be all end all solution. And heck, there may even be better solutions out there. Moving enemies is a big task for this game. There are almost 2,000 in the small scene I'd created. I needed to balance several things, but two of them being the game's frame rate to ensure that there was no stuttering or missed frames for processing, and the smooth movement of all the characters. I naturally started with the easiest solution, which was making each enemy responsible for sending out its own packet of data to the clients for every frame. For those who don't know what a packet is just a bunch of data with a header, including who the packet came from and what type of packet it is, and then a body, which contains all the data that is agreed to by both the sender and the receiver. Having each enemy send out its own packet came with big drawbacks. The first of which was that the host would send out so many packets per frame that it would cause a whole slew of other things to go wrong, such as missed processing of frames and late or missed incoming packets from players. The reason for this is because the game engine would run important processing 60 times per second. On the higher levels, 2,000 enemies would send a packet 60 times per second. That means 12,000 messages were sent out to each client per second. This was far beyond what mine or any other normal computer could reasonably do. The solution I came up with was called the packet bundler. The packet bundler allowed enemy positions to be grouped into a single packet. When the enemy needed to move, it would tell the packet bundler which enemy is moving and to where. Then at the end of the frame, the packet bundler would send off those pieces of data in a single packet to clients. This was great. The enemies were moving fine, but there was another problem. This worked great for a small number of enemies, but when I scaled up to larger numbers, I noticed the packets would fail to send. After some research, I found out there are size limits and fragmentation of packets once you get to a certain size. So I decided to build a chunker. Because I knew the limit of each packet, I wrote some code to break up each of those enemy positions into groups up to but not over that byte limit. And voila, it worked great. Until I needed just a little bit more. The next thing I did was to control which enemies really need to be moving at a time. The game doesn't need enemies in the middle of the spiral moving, animating and performing physics calculations when no player is even close. The way I decided who should be moving was by creating regions in the map. Each region would be responsible for knowing which players and enemies are in each region. I wanted to make it so all regions adjacent to the one a player was in would have active enemies. Active meaning that they would display animations, perform movement, detection, and path calculations. This tremendously reduced the load on the system, especially for lower tier computers like mine. The decision to update each game object at 60 frames per second was originally decided because I saw it gave the clients the smoothest movement. On the level with hundreds of active enemies, the game would still spend way too much time performing physics calculations and rendering for the enemies. Using the profiler built into Unity, I was able to see that I was missing the 16 millisecond time often. I knew that the game did not need to be updating at such a high frame rate for this type of game, so I decided to lower the frame rate down to 30. And now we get to player movement. I've made so many iterations of this that I won't go into all of them, but I will tell you the biggest changes I did. So I initially started with the player's game objects having rigid bodies. The current movement system requires the player to click a location and the character will follow. Similar to RTS games like Warcraft, StarCraft, and others, I started by lerping or linear interpolating the player to the position. This immediately became a problem because when I clicked across the wall, the player would get stuck on the wall, so I needed a pathfinding solution. I found two great solutions for this. One of them was using the A-star algorithm. A-star is a way for the computer to calculate a path given the set of areas the player is capable of walking. The second solution was using Unity's built-in NavMesh and NavMesh agent solution. They both seem great, but I decided to use the NavMesh agent mostly because I wanted to learn how to use it. That's really it. I hooked it up and it worked great for single player, but now I needed to tell the clients where they were. So I decided to add the player positions to the packet bundler, as well as to avoid the same problem I was having with the enemies. Every frame, I would have each player tell the packet bundler, and it would send off all the players' movement data in a single packet. The client would forego using the NavMesh agent to move and solely rely on the position packets from the host. I ultimately decided that I was okay if the player didn't have the absolute most perfect position state. And so I decided to remove the packet bundler sending the positions of each player from the server. I would instead let the player's NavMesh agent do the movement for each of the clients. What this basically means is that the client and the server have two separate states and their positions could be slightly off. But this was a trade-off I was okay making for the smooth movement of the players. I was able to do this because the client is always setting the target location to the server, and the server relays that target to the rest of the clients. The other clients will then have the NavMesh agent calculate and move to the target position. The only thing I truly have the server calculate is the collision between the game objects, and for right now, the gameplay is very smooth. Something I may need in the near future is to synchronize the client's player position with the server. This can be done on either a time basis or an event basis, but I'll get to that when I'm able. This would be needed, for example, when there are missed packets. It would cause a small jitter, but would still be better than what I previously had. Hopefully this was entertaining and maybe you learned something from it. Like the video and let me know what you think in the comments. Also, go wishlist Pandarunium on Steam and try out the demo. I'll leave a link down below. Thanks for coming to see me, and yeah, Curtis.